This continues with the method of corners, graphical solutions, presented in terms of applied problems in Chapter 3. So second example is going to be a minimization problem. Industrial biology owns 2 factories that produce anthrax vaccines and measles vaccines. The factory in America costs $14,000 a day to operate, and it gives 50 units of anthrax vaccine and 3,000 units of measles, mumps, rubella vaccine per day. The British factory costs a little bit more to operate per day, but it's creating the more expensive 75 units of anthrax. It only produces 1,000 of the measles. Together, the U.S. and British governments require 650 units of anthrax vaccine for first responders and 18,000 units of measles, mumps, and rubella for their populations. How many days should each factory be run open to produce the correct number of units while minimizing costs? We're going to use our same idea that we're going to find this feasible solution set area. We're going to find the corners, and we're going to use those corners to find things. But before we do any of that, I have to read through the problem and figure out what are the equations I'm talking about. I'm talking about costs. It says minimize here, but common sense tells us we're minimizing cost. So I talk about minimize, and again, we have our subject to. If you get used to taking word problems and converting it into a common format, this one, and then you get used to taking this format and solving it, no matter what technique you use to solve it. Here we're using method of corners. It makes the whole process very much plug and play. So get used to having a little bit of what I call paper organization. If you know what you're looking for, you know if you found it or not. So I have to talk about minimizing. It's a cost equation I'm minimizing instead of profit, so I'll call it C. And what am I asking for? How many days should the factories be open? So let's call the American factory number of days X, and let's call the British factory number of days Y. So then I know my cost. I want days, so that has to be my variable. X and Y are in terms of days open. X for one factory, Y for the other. Now I know my costs. 14X plus 16Y. This is my cost equation. This is the function I'm going to be tackling. And notice I changed the thousands into 14 and the 16,000 into 16. I'm doing this in units of 1,000. So whatever my final answer is, I'm going to have to tack on 1,000 to that. This is very common. In industry, you usually deal with numbers being in millions or billions. What are my constraint equations? Well, once again, I have non-zero variables. The American factory has to be open a non-negative number of days, as does the British factory. It can't work any other way. But now we have some information about these factories. Let's talk about anthrax first. I need at least 650 units of anthrax. Whatever I put over here on this side, I have to make sure that this left side is bigger than the 650 or equal to it. So this is the way my inequality is going to go. If I have less than or equal to 650, I might not have the 650 units I require. It's okay to overproduce a little bit. That's acceptable. But I need to make sure I have at least 650. This is a minimization problem. What have I got? Well, the American factory produces 50 units of anthrax. Remember, we're doing everything in terms of 1,000, so it's 0.05 times the number of days the American is open, plus 0.075 times the number of days the British factory is open. On the other hand, for the measles, mumps, and rubella vaccine, I need 18,000 of them. Remember, we're doing things in terms of decimals, in terms of thousands rather, so it's going to be 18. I again need to be bigger than or equal to this 18. And the Americans can produce 3,000, while the British only produce 1,000. The British are more specialized on anthrax. The Americans seem to do better on the measles, mumps, and rubella. So I've created my system of equations. Once I have this system, then I can solve it. So from the word problem, you get your equation system. From your equation system then, let me see if I can get all of them on here. First I need to take these guys and create a graph. We're using corner method. So let's do that. I'll take this top guy and graph him out. When I'm graphing out the top part, I don't know, I'm going to solve it. So I'm going to get 0.075y is bigger than or equal to negative 0.05x plus 0.65, getting it to mx plus b form. If I solve this just a little bit more by dividing both sides by 0.075, I'm going to get y is bigger than or equal to negative 2/3 x plus 26/3. I would be using a calculator to be doing the division here. You can check my work here, but it's good. All right, so on my little graph here that I've got going on the left, oops, let me try to get the color that'll show up nicely. Here's my x-axis, here's my y-axis, and let's put all the things in units of 5, 5, 10, 15, 20, 5, 10, 15, 20, this is 20, 20. So my y-intercept is 26/3, which is about 8.6. So that's going to be a spot right here. And then if I go and I plug in 0 for y and solve this out for x, I'm going to find that I've got an x-axis value of 13, which is just a little bit past 10. So I've got this line. Again, it's a solid line, not a dashed line, because this is bigger than or equal to. And this time, if I use my test point idea and plug in 0 and plug in 0 here and ask, is 0 bigger than or equal to 26/3? The answer is no. So I plugged in a test point over here. I got no answer, so I'm shading off this side of my graph. Again, I'm going to just do the shading very, very lightly because I'm about to erase all those and use the yellow highlighter again. For my second equation, I solve this for y. Y is going to be bigger than or equal to negative 3x plus 18. And that gives me a y-intercept of 18, which is almost up here at 20. And then if I talk about my x-intercept, that's going to be an x-intercept at 9, which is just under here. Again, it is a solid line because this is bigger than or equal to. And again, if I try my test point idea, since 0 is not bigger than 18, I'm shading to this side of this line. I also know that I've got these positive numbers here. Now again, I'm going to erase this area. See where the common highlighted area is, where I've got these double-crossed areas? That's where I'm actually highlighting. Let me do the highlighter on it to emphasize very clearly what part of the graph we're talking about. I'm in this bigger region. I can't go to the left of this initial y-axis line here because x is always positive. If I went over here on this left side, x would be negative. I can't go below this line right here because if I went lower down here, y would be negative, and y is always positive. And then I have to stay to the left of this one line here, and now I have to stay to the left of this one. Notice, unlike the last time, and this is fairly common for minimization problems, I've got something in this region where I can go as far to the right and as far up as I like. I won't go too far because I don't want to shade in my entire screen, but this is called unbounded. Once again, this is my feasible solution set, capital S, but this time it's unbounded. That will become interesting a little bit more later. And this time, we've got these as my corners. Here's a corner, here's a corner, and here's a corner. These are the only corners I have. Notice this time the origin is not one of my corners. So, I don't know, I've got corner A, I've got corner B, I've got corner C. So as I start to figure out what's going on with A, B, and C, I know some things about these. A is up here. I know exactly where A is. It was at 0x, and it was on the y-axis, and it was up there at 18. That's how I initially drew that line. And then for C, I know some things about C as well. It's at 13 and 0. Again, it's how I initially drew that line when I solved it out right here. Okay. So, I'm ready now to talk about B. B is a little bit trickier. B is where the two lines intersect. So I've got my two line equations, 0.05x plus 0.075y is going to be, and since we're trying to find out where they're equal to, we stopped talking about inequalities, it's going to be 0.65. And then I also have the second equation, which was 3x plus y is going to equal 18. This one I'm not going to solve using addition method because it looks a little harder. Instead, I'm going to put it in an augmented matrix and solve it that way. So I got 0.05, 0.075, and then 0.65. And then I have 3, 1, and 18. Again, there's lots of different ways I could solve this. I'm going to try to do a way that avoids dealing with decimals and avoids dealing with fractions. So the first thing I'm going to do is multiply row 1 by 40. If I multiply row 1 by 40, I should get 2, 3, and 26. And on the bottom, I continue to have 3, 1, and 18. Next, I'm going to swap row 1 and row 2. So I'm going to have 3, 1, and 18. And 2, 3, and 26. I seem to have a personal preference for trying to do all my different row operations. That's just me. So I've done the multiplying a single row, I've done the swapping. The only other row operation we've got left is adding and subtracting the different rows together. So now we're talking about pivoting. I want to turn this into the number 1, and I want to get this guy, that's a 2 right now, to be 0. So I'm going to do row 1 minus row 2. Because 3 minus 2 will give me 1. That means row 2 doesn't change. And 3 minus 2 leaves me with 1. 1 minus 3 is going to leave me with negative 2. And then 18 minus 26 is going to leave me with negative 8. I've got the 1 where I want it, so now I'm going to do row 2 minus row 1. Top row is not going to change. 2 minus 1 is going to leave me with 0. 3 minus a negative 2 is going to leave me with, excuse me, I can't count. Row 2 minus 2 row 1. That's what I would want. 2 minus 2 times 1 is going to give me 0. 3 minus negative 4 is going to give me 7. And 26 plus 16 is going to leave me with 42. Next, I want to pivot around this guy, so I want that to be a 1. If I do 1/7 times row 2, the top row is not going to change. The bottom row is going to be 1/7 times 0, which is 0, 1/7 times 7, which is 1, and 1/7 times 42, which is going to leave me with 6. Finally, I want this right here to be a 0, so I'm going to do row 1 plus 2 row 2. And that's going to leave me with my final answer of 0, 1 is going to leave me with 1, negative 2 plus 2 times 1 is going to leave me with 0, and negative 8 plus 12 is going to leave me with 4. This answer right here, because this was my x column and this was my y, tells me x equals 4 and y equals 6. So I take that information right back up here. X equals 4 and y equals 6. Now I've got my 3 points. These are the only 3 corners I have. Remember, our theorem tells us that my cost equation is going to be solved on one of those corners, and my cost equation being 14 times x plus 16 times y. So here are my costs. When I plug in 0 for x, I get nothing. When I have 16 times 18, that gives me 288. Down here, if I plug in 13 and multiply it, maybe I should recopy my cost equation. It's 14x plus 16y. So 0 in for here gets this part away. 14 times 13 is going to leave me with 182. And finally, this cost, if I do 14 times 4 plus 16 times 6 it's going to leave me with 152. Remember, these are in dollars. These are the actual costs, and these are in thousands of dollars. These are costs, so I'm trying to minimize, which tells me this guy right here is my minimum answer. So this will produce the correct number of anthrax vaccines and the correct number of MMR vaccines while making my cost be the least bit possible. If I only ran the British factory, it would cost me $288,000. If I only ran the American factory, it would cost me $182,000. And if I did any other sorts of points in between here, where I would run some different combination of both of them, it would still cost me more than this one, because the optimal solution is going to happen at the corners. So my answer is America should run 4 days, and the British factory should run 6 days. And that will get me my solution for this. Again, if you're having questions, shoot me an email, and you want to break up this problem into 3 parts in your thought process. 1 part, reading the words and getting out the initial setup. Next, taking the setup and creating the graph. This is section 3.1. Finally, taking that graph and the setup, tying it all together, maybe having to use some of the information from the previous sections to solve out where one of the lines cross, and getting your final answer. So shoot me an email if you're having trouble. Tell me where you're having trouble. Tell me what's giving you trouble, and we can get this working for you.